Hello, everyone. Welcome to our final project presentation. Our project is a custom compiler build, and our main goal for this project was to understand how compiler work, how high-level source code is converted into low-level machine instructions. Our next goal was to take what we learned in the class and use it to build a project that shows how a compiler works, starting with reading the code, breaking it down, building the AST, and generating machine code. So the tools we use for Python and the PLY library, which stands for Python, Lex, and Yak. We also use the C-style language that outputs MIPS32 assembly, which run using the Mars simulator. So, what does our compiler do? Our compiler builds an AST to represent the program structure, which is then used to either execute the program directly or generate MIPS assembly code. Using PLY, we define grammar rules for statements like, for example, let A be 5, and while x is greater than 0, do, which are translated into AST nodes eventually into assembly. The compiler supports features like variable assignments, arithmetic expressions, print and write line, if else and while loops, and user input through readInt. So let's look at our example of how it works. First, the user can input an integer, then the program uses the integer to compute the Fibonacci sequence. As you see, in our example, we used number 9. You can see how the program also generates an AST. It's noticeable that our AST looks a little different, but it's only about the structure. We use the dictionary-based AST because it's easier to generate, inspect, and process during interpretation and generation. It efficiently stores node types, values, and children in a simple recursive structure. We understand that it's not visually pretty, however, it's functional and flexible for our project goals. Now you see how the source code is turned into MIPS instructions like li, add, back, and syscall, which run inside the Mars simulator to verify that the output is correct.
So, our challenges and solutions. At the beginning, our biggest challenge was simply understanding what a compiler is. We didn't know what the final output should look like or how to test it. So, we spent time researching existing examples online and breaking the process into steps. One of the hardest technical parts was simply implementing the while loop for Fibonacci numbers. We struggled to get the condition to work correctly in both the AST and the MIPS output. Eventually, we fix it by adjusting how we handle labels and jumps in MIPS. We also had troubles debugging ply rules, especially because syntax errors weren't always helpful. We solved this by carefully checking our grammar rules and adding more print statement to trace how tokens were processed. So, our achievements. The final result is a working compiler that successfully translates high level C style code into MIS assembly. It builds the AST, interprets it, and generates runnable outputs in Mars. Personally, we learned so much before this class. We had no idea how compilers work. Now we understand how the front end, like Lexer parser, connects to the back end, like code generation, and we've written code that brings all of it together. This project also taught us important programming skills, modular design, debugging, and how to break down complex logic into small, manageable steps. We're really proud that we also created a mini language of our own in the process. So, as a future application and reflection, I we think that this project gives us a deeper understanding of how software works. These skills are also useful for software development, security, and tool building in the future. We've gained confidence in solving hard problems, and the patient persistent we will have and develop definitely help us in the future coding or research projects. So, thank you so much for watching. We hope you enjoy our projects and learn something new.